Welcome back everyone to Workshop 4, which will focus a little more on the coupling constant and its applications. In the previous workshop, we learned how to measure the coupling constants of the signals in an NMR spectrum. We did not, however, concern ourselves too much with the information specific J values could tell us about structure. Let's consider a tri-substituted alkene, for instance. In this case, we have three different types of protons labelled A, B and C. Despite the fact that protons B and C are both attached to the same carbon atom, they are in fact inequivalent. We call hydrogen atoms separated by two bonds geminal hydrogens. The geminal sp2 hydrogens in this example will resonate at slightly different frequencies because they exist in slightly different chemical environments. This will be reflected in the coupling constant between Hb and Hc, as well as in the coupling constant observed between each of these protons and Ha. Significantly, the trans coupling constant is greater than the cis coupling constant, and we can therefore use such information to distinguish between geometric isomers. Also note that the geminal coupling constant is particularly small. This is generally the case for inequivalent geminal protons. In this example, we have a di-substituted alkene which may have cis or trans geometry. Coupling constants can help us differentiate between the two. On the left-hand side, we have two signals, each with a J value of 14 Hz. This is characteristic of trans geometry. On the right-hand side, we have two signals with coupling constants of 9 Hz, which is characteristic of cis geometry. In this example, we'll analyse the proton NMR spectrum of the aldol condensation product dianisal acetone, using coupling constant data to determine whether geometry around the double bond is cis or trans. Here we see the NMR spectrum for the compound, but let's expand this region to take a closer look. The signal which is furthest downfield is a doublet with a particularly large coupling constant and corresponds to proton A. If we measure the exact chemical shift of each peak in the doublet, subtract one of these values from the other, and multiply the result by the operating frequency of the spectrometer, we get a value of 16 Hz. This is consistent with trans geometry and thus confirms the proposed structure provided alongside this NMR spectrum. Here we have some common couplings and their associated coupling constants. In particular, note that we can interpret similarly useful structural information from the coupling constants observed between aromatic protons. For orthocoupling, J values between 6 and 9 Hz are typically observed, whereas for the longer distance metacoupling, much smaller coupling constants of between 1 and 3 Hz are observed. Careful analysis of the signals in the aromatic region of proton NMR spectra can thus aid inferences on the substitution pattern of aromatic compounds. Now try the following learning activity for yourself, selecting your answer in the appropriate part of the form below. Let's round off our discussion on coupling constants by taking a short look at a model which describes coupling constants in saturated compounds. The Karplus equation relates the dihedral angle between two inequivalent vicinal protons with the coupling constant between them. We needn't concern ourselves too much with this equation. The curve described by the equation is much more useful. Do take note, however, of what we mean by dihedral angle, as indicated in the Newman projection here. From the graph, we see the maximum and minimum coupling constants predicted for vicinal couplings. Such J values range between approximately 2 and 13 Hz. This relationship stems from the fact that coupling occurs through bonds. J values are at their largest when the CH bonds are either syn or anti-periplanar. In other words, when the CH bonds have a dihedral angle of either 0 or 180 degrees. The Newman projections illustrate these angles as observed when looking down the carbon-carbon bond separating the two vicinal protons. When we have freely rotating carbon-carbon bonds, like in a straight chain alkane for example, the coupling constant observed will be an average value, as the dihedral angle between vicinal hydrogens will be constantly fluctuating at room temperature. This is illustrated here by the appropriate Newman projections. However, this is not the case in all systems. In cyclic compounds, where there is no free rotation around carbon-carbon bonds, dihedral angles remain fixed, so we have a different situation. In substituted cyclohexanes where ring flipping is prevented, for example, there are two different types of proton and therefore two vicinal coupling constants may be observed due to the non-equivalence of the axial and equatorial protons. For two axial hydrogens, the dihedral angle is 180 degrees and therefore a relatively large coupling constant of 8 to 14 Hz is observed. For two equatorial hydrogens, the dihedral angle is 60 degrees and therefore a smaller coupling constant of 1 to 5 Hz is observed. Finally, when we have one equatorial and one axial hydrogen, the dihedral angle is also 60 degrees, so we see a smaller coupling constant of 1 to 5 Hz. You can now attempt a final learning activity on the form. This marks the end of video number 4.